Okay, so let's look at an example of how RMA use median polish to estimate the expression index. In here, the rows are the samples and the columns are the probes. Ideally, when you run RMA, you want more arrays, 6 or 10 or 20 arrays or samples at a time. For example, I'm only going to show you 5 samples. For the probes, we have 10 or 20 or 15 probe, perfect match probe, but I'm only showing you 7, but just you get some idea. So this is the probe value that is for the first sample. And these have been quantile normalized and logged already, okay? And this is the probe value for the different samples. So in the very first step, we take a median of every sample across all the probes. This is assuming all the probes are equally good, right? We just take a median. And to estimate the expression level of this gene in the first sample, the median is 12, and the median of the second one is 13.7, and so on. So we get a median level of all the samples. And you get also the very bottom here is the median of this last, this is like the average expression across all. This one is not as useful in here, okay? So this is, in terms of ranking professors, initially you are assuming all the students are equally good and just average or the median of their ranking for each professor. The next thing we look at is we will subtract each of the original value by their median. And so 7 subtracted by 12 will be -5. 8 subtracted by 13.7 is going to be -0.57. And so basically, every probe value you subtract by the current ranking or current value of the expression. And so here, after this, this is the matrix you get now. And from this, what you can see is that the first probe, rank professor is very harsh. They always give everybody, like a professor, a bad score in some sense, right? So most of the probes, most of the samples in here, well, all of the samples in this case, get a negative value. Whereas the fourth probe is a great inflation. Every professor gets a good score, right? So you have a very positive value. So in the next step, what we're gonna do is we're gonna estimate the B, which is the probe effect, by taking a median across the column. So here we have, -5, -5.7, da, da, da. We calculate this. The median of the probe. By the way, once we have this value, we also replace this by this thing here. I'll show you why this is the case. This is the final expression estimate that we have. And this one is the final probe effect that we have. Okay, initially we assume they are all the same. There's no adjustment. Initially it's 0. Then, so also initially we don't know how the genes are expressed. Initially it's 0, but after we have this, we replace the original, or we kind of add to the original 0 by this current estimate. And so here we subtract, we estimate the median of every probe now. And in the next step, we replace this row by whatever our current estimate of the probe effect into here now. And then we subtract the original value, -5 by -5.8. And so now it becomes a little positive. Okay, so each of the original probe now, not the original, this level of probe level is subtracted by the median of that probe. So you adjusted the probe, and this common penalty is added at the bottom in some sense, okay? And then at this level, we're going to, again, reevaluate the median of all the probes on this array. And now this is the median of all the values in here. This is the median for the second, the median for the third. And we are going to add this value to the original expression index estimate. So remember previously the expression index is 12, but now we adjusted a little bit more. We give it another 0.8. You know, previously this gene is expressed at 13.7, but plus another 0.3, now it's expressed at 14. Okay, this gene, yeah, you can see here, previously it was expressed as 13, but now the median now is -1. So we add that -1, now is 12. Okay, and then we subtract this level by this residual kind of expression index, and that's subtracted in here. And based on this, we estimate the remaining probe effect, and that's in here, in this yellow column here. Okay, that's the median of all the columns for that probe effect. And so then we now add this residual probe effect to the previous probe effect, which is in here. And now this is the updated probe effect. Okay? And then we subtract the original probe by the remaining probe effect. So 0 minus -0.2 is going to be 0.2, right? 0.2 minus -0.8 is going to be 1, and so on. Okay? And at this level, when we calculate the median, voila, everything is 0. It means we have corrected everything. Okay? And so at the end, what we will get is the expression index, which is the expression level of this gene across the 5 samples. We also know that these probes or these students have their respective biases. This probe is usually very low, and this probe is even worse. This probe is okay, and these 2 probes are very high. And so if this one here, we are looking at the original probe value. And you can see here, probe 1 is pretty low, it's -6, and the second probe is probably even lower, or roughly the same, you know, around the -6. The third probe is at -5, and the fourth, fifth probes are very high. Their probe effect is 3 and 4. The next one is 1.7, and the last one is 0.2, is kind of a little bit lower. Okay, and the expression level, you can see series 1 is that first sample. It's this blue one here. Its expression index is estimated around 12. The second sample is the red one. You can see every location, well, most of locations is pretty high. It's estimated about 14. And this one is the highest. It's a purple sample in here. It's estimated at 15.1. And the lowest one is this 12, which is 5th. Yeah, the 5th is, you know, towards the end is okay, but in the beginning it's very, very low. And so you can see in a few iterations, we are able to estimate the probe effect and the expression index of this gene across multiple samples, which roughly represented a good summary of all the probes. Okay. And I have another example. I'm going to put both examples online, and you can play around with it. You can see the equations. It's very simple. Okay, so play around with this, and you can see usually 2 to 3 iterations is all you need to make the columns and rows to be 0. And once you have 0, the expression index will not change. The probe effect is also estimated. Okay, so median polish is every time you calculate the median, you shave it out from the original value, and you update your expression index or update your probe effect. All right. So that's why RMA is kind of fast. And we go back to the presentation in here. So how did the RMA, or as a method when it's published, how did they convince the community that this is really the right algorithm to use? They use an experiment called the spike-in. So supposedly you have the same RNA, you split in half, and in one of the sample, you added some other RNAs in there but it's just a few genes. I think from, in this case, 1 to 11, you added 11 genes in here. The RNAs are added at known concentrations, but across slightly different range. And so you compare the samples. So the original sample plus the original sample with a few of the spike-ins, okay? And you use the mass4 to estimate the expression index of that sample and then the other sample, or you use RMA. Of course, with RMA, you use more than 2 samples. You usually take 10 samples, but you can compare 2. After you get the expression index of every gene across the 2 samples, you can run the MA plot. You want to ask, so the x-axis, which is A, is the average expression level of this gene, or the geometric mean of the gene, and the y-axis is the difference of expression that you measured across the 2 samples. So remember, this is initially identical sample. So except for the few spike-in genes, you expect the expression level to be estimated to be identical, right? They shouldn't be different. And so if you look at, so each dot here is 1 gene. And if you look at RMA, when the expression level is high, it's okay. But when the expression level is low, there's a lot of noise in the estimation. Because, you know, like you're dealing with really background noise now. It's not doing a very good job. But with RMA, you can see it's really good. You know, it's really on the 0 line, very little noise, and only things that are different are the few spike-in samples that you added in here. Then you can imagine if I want to compare cancer versus normal or some drug treatment differential expression, you can trust that the ones that are called different are really different. Whereas in here, you will call a lot of genes as being different between the 2 conditions, which are fake. Right? So using RMA, you can also look at the differential gene expression, and you can see how the, you know, like RMA does the normalization or the expression index estimate accurately, and then you can trust that the differential expression you get is pretty good. Okay, so in summary, when you have a Affymetrix expression, you will have a cell file which give you the raw data and the CDF file, which is the design file telling you which probes belong to the same probe set. And we talk about normalization. LOS is kind of this, try to normalize a nonlinear curve, but quantum normalization is really very popular that people use for many normalizations. The very important assumption is that you assume most of the probes on this array measures at a similar level. They should give you no difference between the 2 conditions. In order to know whether you are normalizing it well, you use the MA plot to look at the difference of value across a different range of concentrations. And this should be close to the 0 line if the normalization is correct. And for expression index, which is you summarize all the probe set into a single number to look at the expression level of a gene in that sample, we use this robust multi-chip analysis, which includes, first you correct the array background, you do quantum normalization, you take log, and then use this median polish iteratively estimate the probe behavior and the expression index. And at the end, you will get an expression index, and that is at the log scale. So at the end, if you look at the levels, you can see here, this is the mass4 value. The value is between, you can see there are some expression index that are like negative. And then there's like a 10. But for RMA, usually the expression level you get is between like 5 to 12 or something like that. So a lot of these very low values, these are just genes not expressed at all. So usually below 5, you expect it's not expressed. Okay, so now with Affy array, you will get a big matrix. Each of the rows is a gene now or a transcript, depending on the CDF, and each column is a sample or a condition, right? So you'll get a big matrix of numbers, which is more manipulable, more understandable. The original file is, the cell file can be in a text file, which is bigger, but you can also zip it into a kind of a binary file. But that file has like 6 million rows. which is impossible to read, right? So RMA, you will see in homework 1, you will start from a cell file and you will generate an expression matrix. You'll see how that's done. Okay, questions? All right, we'll finish today.